So we were looking at Richardson extrapolation, and we were basically trying to figure out how to eliminate the various Ks, because the Ks are the coefficients of the H's. So as you eliminate each K, then you eliminate a power of H, which means you decrease, well, you increase the order of the approximation and decrease the error of the approximation. So we found that we were able to write N1, M is N1. So N1 is whatever your initial approximation may be. So for example, up here, it could be N1 could be first order forward approximation. And then I want to figure out a way to take that approximation and make it have a higher order approximation or a smaller error without having to rederive a new formula. So we figured out how to find N2, then we figured out how to find N3, and then as we kept doing this, we were able to get a pattern to get N4. And so in general, we had something that looks like this. And so the general formula allows you to approximate the your original n as an order of h to the j. So whatever you want your j to be. And if you know that your formula actually goes in powers of 2, so it looks like h squared, then something h to the 4th, then something h to the 6th, etc., then there's another formula that can be used. So the other general formula is if your M looks like N of H, and then it's K2H squared plus K4 H to the 4th plus K6 H to the 6th plus dot, dot, dot. So if you know that it's skipping by powers of 2, then you can use the other formula that is Nj of H is equal to Nj minus 1 of H over 2 plus Nj minus 1 of H over 2 minus Nj minus 1 of H. And then this becomes 4 to the J minus 1 minus 1. And this is an approximation of order H to the 2J. Okay, so we did an approximation earlier, so I need to go back and find it. It might, yep, it was in numerical differentiation. It was my last example, I believe. Here it is. So this was a central difference approximation. So we used the centered difference approximation. And so I'm just going to grab this just to remind us of the example that we did. And I'm going to move this over to Richardson extrapolation. Okay. All right, so in general, when we're doing this, you create a table. So this is what your table looks like. So if you create this table, then you can use this table to find your new approximation. So I'm going to draw a simple line here. And then this is order H. And so you will compute first N1 of H. So you will do that first. Then you will compute N1 of H over 2. Then you will compute N1 of H over 4. And then N1 of H over 8. Okay, so now that I use those, then for order H squared, I need to compute N2 of H. And to compute N2 of H, I need the two previous ones. And then I'll need N2 of H over 2. And then N2 of H over 4. So that I can get an order H cubed approximation. So that'll be N3 of H. And I will need to find N3 of H over 2 in order to get an order H to fourth approximation, which would be my N4 at H. So the order that we do them in is the order that I wrote them in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we finally get to that. Okay, so approximations actually are generated in the order indicated by the circle numbers that I have put on the paper. Okay, so here's our example. So our f of x is x e to the x. Our f prime of x is equal to x plus 1 e to the x. And we found f prime at 2. And we said that that was 22.16719. Okay. All right. So when we do, let me see, I think what I have here. Just want to remind us of what we did before. Yeah. Okay. Yep. Okay, so we did a central difference approximation. And for our central difference approximation, we use that. And if you remember, our formula is that f prime of x is f at x plus h minus f at x minus h all over 2h. And then actually that's minus h squared over 6, this triple derivative of x, and then minus h to the 4th over 120 times the 5th derivative at x plus dot, dot, dot. So as you can see, these skip by 2. Okay. So here, our error formula contains only even powers of h. So let's extrapolate to get a higher approximation with a smaller error. Okay. So we know that x naught that we're looking at is 2.0. And then our N1 at H is F at X naught plus H minus F at X naught minus H all over 2H. So this is our N1. I didn't have to rewrite it, but here it is. This right here is N1 at H. Okay, so now we need to find, so let's create our table. So from up here, we just want to go, order, where's my table here? We are going to go, this thing skips. So we have N1 of H, N1 of H over 2, and N1 of H over 4. Okay. And then that should be, so N3 should have N3. I'm a little confused. Give me a second here. Why am I doing N3 and not? Oh, yeah. Okay. So here's my table. So I already know that my approximation is order H squared. So that's N1 at H. Then we're going to need N1 at H over 2. And then N1 at H over 4. Then we're going to need N2 at H and N2 at H over 2. And then we can end up with N3 at H. And so for us, N3 at H will be of order H to the 6. So therefore, we will have F prime. This will give us F prime of 2.0 equal to N3 of H plus order H to the 6. This is order H to the 4th. And this is order H to the 6. Okay. So N1 at H is just N1, and H was, oh, I didn't tell you. H is 0.2. Okay. So N1 of H is just N1 of 0.2. So that's going to just be F of 2 plus 0.2 minus F of 2 minus 0.2 all over 2 times 0.2. And that turns out to be 22 plus 0.41416. Whoa, 414160. Okay. And then we compute N1 of H over 2. So N1 of H over 2 is N1 of 0.1. And that just turns out to be 22.228786. So now we found number 2. So this one was number 1. This one was number 2. This one's number 3. So this one was number 1. This one's number 2. So now for number 3, we need N1 of H over 4. So that's N1 of 0.05. And so that turns out to be 22.182564. Okay. So now that we've computed that, we've computed the first 3 terms. So now we can compute N2. So N2 of H, which is our 4th approximate here. This is simply N1 of 0.1 plus N1 of 0.1 minus N1 of 0.2 all over 3. And we know each of these. We know N1 of 0.1, we know N1 of 0.2. And so now notice I'm not doing any more calculations with the approximation. I'm just using the values that I have. So this I can just compute to be 22.166,995. Okay. So next, so that was number 4. And now in order to do N2, so now number 5, I need to do N2 of H over 2. So that's N2 of 0.1. So that's N1 of 0.1 over 2, or 0.05. plus N1 of 0.05 minus N1 of 0.1 divided by 3. And this turns out to be 2.22.167.157. Okay. All right, so now to get our last value, if you notice, we're using this formula. So here at the N3, where am I? Right here, I'm going to use 4 to the 3 minus 1 because they skip by 2's. So since I know it skips by 2's, I'm using the second formula. So I'm going to get 4 to the 3 minus 1, which is 4 squared, which is 16 minus 1. So I'm going to have a 15 in the denominator. Okay, so for number 6, I now have N3 at H. And that's N3 at 0.2. And that's going to be N2 at 0.1 plus N2 at 0.1 minus N2 at 0.2 all over 15. And so now N2 0.1 plus N2 0.1 minus N2 0. So this is now 22.167.168. Okay, so our original approximation to the derivative was 22.414160. That was our original approximation. And so now we've been able to use Richardson extrapolation to get an order h to the 6 approximation without having to find the order h to the 6 formula. And now look at the error. So this is the true value. The true value, whoa, 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 whoa. Is up here, 22.16719. And we originally started at 22.4161141160. And now we're down to 22.167.168. Okay. So that is Richardson's extrapolation, and it works really nicely. It's a pain because you have to keep doing the table, but if you start off with a poor approximation and you want a better approximation and you don't want to rederive a formula, Richardson's extrapolation is the way to go. Okay, any questions about that? Okay. All right, so we're going to go on to numerical integration. And numerical integration, you've all done it. There's nothing new and spectacular about this. We are going to do some cool stuff in this section, other than trapezoidal rule and what is it? Simpson's rule, et cetera, et cetera. Okay, so let's just talk about some motivation for this. All right, so motivation, there could be several things. This could be part of your research that you come upon an integral you just can't do, or it could just be as simple as wanting to find the area under the curve. Okay, so we want to evaluate, so our goal is to evaluate a definite integral. All right, so we all know what that is. That's the integral. I is equal to integral from a to b of f of x dx. So I have some function and it looks like this. Okay, and from a to b, we're looking at the area under the curve of this particular region. So we're looking at the area under the curve of that. Okay. Now the thing is, this integral is not always easy. Okay. One of the most difficult integrals to integrate is the integral of e to the negative x squared. All right, which is the Gaussian, and being able to use that for the normal distribution in statistics. I can't integrate integral from a to b of e to the negative x squared dx. If I had an x there, yes, but this is not integrable. So somebody who has used these integration rules to be able to come up with tables so you can evaluate that in statistics. So let's look at the definition. I want to do a definition first. So this definition is called quadrature. And quadrature is the process of constructing a square equal in area to a given surface. Okay, so let's start off with some basic quadrature rules. Okay, so the first one is the midpoint rule. All right, so the midpoint rule says we're just gonna, we have this function and we have whatever it looks like here, and we're trying to find the area between A and B. So okay, so the midpoint rule says, you know what? Here's A and B. Find the midpoint between the two of them. So here's the midpoint. Uh-oh, what did I just do? I feel like I just did something. Oh, okay. Find the midpoint between the two. Okay, now I know what the problem is. Okay, so find the midpoint right here. A plus B over 2. And then go up here. That height is F of A plus B over 2. Draw a line. Of that exact height. And say, this is going to approximate the area. So I'm just going to take the midpoint of the interval as such. And when I take the midpoint of the interval, then my integral, which is the integral from A to B of f of x dx, is going to be approximated by the height, which is f, well, by the width, which is b minus a, times the height, which is f of a plus b over 2, plus whatever error comes my way. That's the midpoint rule. Okay. Then we have the trapezoidal rule. Trapezoidal rule says, let's take the same region. Okay. And this time I'm going to draw a trapezoid. So I'm going to start from this point here. And I'm going to draw a trapezoid between A and B. And then the area is everything I get inside the trapezoid. Okay. So we know that if I draw a simple line right here, that is not where I want that line to be. Good. Okay. So the area of the trapezoid, we know, oh, I don't even need to draw that line. Let me just bag that and forget it and go through all that crazy extra stuff. Okay, so the area of the trapezoid, well, the area of a trapezoid is 1/2 L1 plus L2 times h, where L1 and L2 are the different heights, okay, or the lengths, okay? So therefore, my integral, which is the integral from a to b of f of x dx, well, this height is f of a, and then this height is f of b. So therefore, this is going to be, and this is this, I'm going to use h to be my b minus a. So I'm going to get b minus a over 2. And then I'm going to get f of a plus f of b plus whatever error comes my way. So as you can see in the first approximation is not good, because in that particular picture, I have not enough area. So my integral is going to be underestimated. And in the second one, my integral is overestimated. So that doesn't work well either. Okay, the third approximation is Simpson's rule, okay? So Simpson's rule says, instead of trying to approximate it using a linear function like the trapezoidal rule, we're going to use a quadratic function. So for Simpson's rule, I think I actually may want to I'm going to keep going. I'm trying to debate if I wanted to change my notation here. Okay, I think I am going to just go back and make these smaller numbers. So I'm going to let this be b. I'm just going to let this be a 1 and a 2 and a 3. I'll be up to z by the time I get done. Okay. All right. So Simpson's rule is we want to connect the endpoints with a quadratic polynomial. Okay. And so let's put my picture back again. Okay, so here's my picture. So this time I want to connect this with some kind of polynomial. So let's say there's a quadratic function that looks like that actually approximates it. And then our area is the area underneath the quadratic. That doesn't look good. That looks like a cubic. That's got too many derivatives. Let's just not do that. Let me go back. That's not good. Okay, we're going to try a quadratic. That's better. Okay. Yeah, that other picture was a cubic, and that was not going to work. Had too many extrema. That function only has one critical point. Okay, so again, we're going to use the point a plus b over 2. And so now my polynomial p looks like ax squared. Can't use that a. Got to use capital A. Ax squared plus bx plus c. And so now p of a, which is capital A times little a squared plus capital B times little a plus c, that has to equal f of a. And then p of a plus b over 2 is capital A times a plus b over 2 squared plus capital B times a plus b over 2 plus capital C, and that has to equal f of a plus b over 2. And then last one is capital P of B. Has to be equal a times little b squared plus capital B times little b plus capital C, and that has to look like f of b. And then my goal is to take all of this and solve for a, b, and c. Okay. Then integrate this thing. So my integral is the integral from a to b of f of x dx becomes approximately the integral from a to b of the polynomial that we get, a x squared plus bx plus c, kind of like the last homework that you had to do. And this turns out to be ax cubed over 3 plus bx squared over 2 plus cx, that whole thing evaluated from a to b. So I get my integral is approximately a over 3 times b cubed minus a cubed plus b over 2 times b squared minus a squared plus c times b minus a. And when you work it all out, this turns out to be f of a plus 4 times f of a plus b over 2 plus f at b, all of that divided by 6 times b minus a again, plus whatever error we've accumulated in making an approximation. Okay, so now we understand what our main idea is. Okay, so our main idea, those are the three that you learned in undergraduate calculus, actually. Okay, so the main idea all right, we want to approximate the integral I, be the integral from A to B of f of x dx by evaluating f of x at a finite number of points. Okay, so this is what we're going to have. So I is going to be our integral from A to B of f of x dx. We're going to write it, it's going to be approximated by a sum of points I going from 0 all the way up to some finite number n. And we're going to have weights wi times f of each xi. Okay, so the xi are our integration nodes. And our wi are their integration weights. Okay. All right, so let's go back. We're going to start back for a few minutes using our Lagrange. We want to remind ourselves about the Lagrange interpolating polynomial. Okay, so let's recall for a moment. I really like the way this material builds on what you've already learned. Okay, so remember we had some function f of x, and it was approximated by a polynomial of degree n, depending upon the number of points that we were looking at. And this was the sum I equals 0 to n of Li of x. And then we multiplied by f of xi. And here we had x, a set of points xi, I equaled 0 all the way up to n. Okay. And if you remember, we were able to say that our f of x actually equaled that polynomial. With an error term that looked like the m plus first derivative at some number c over n plus 1 factorial times x minus x naught times x minus x1 all the way up to x minus. And now I got to remember, is it xn minus 1 or is it xn? I'm actually not sure. Ha ha. it is. Okay. All right. So if you remember, each Li of X was the product I equals 0 to N, but I could not equal J. And actually, let me go back and make this J equals 0 to N, because the sum is on J, the product is on J, and J does not equal I. And this was X minus XJ all over XI minus XJ. Yes. Okay. So this was the ith Lagrange interpolating coefficient. Okay. All right, so we're going to use those. Okay, so this new method that we're going to do is called developing Newton-Cotes formulas. Okay, so C is going to be our Newton-Cotes formulas. So everybody up to speed so far? I don't think I've done anything difficult. I think everything has been pretty self-explanatory. Okay, so the last homework that you had to find the Lagrange interpolating polynomial for the sine of 3x. And then you had to integrate that and evaluate its approximation, the Lagrange interpolating polynomial being integrated with the actual function being integrated, and see how well of an approximation or how good it was. And that's kind of like what we're doing now. Okay, so now we want to replace our function f of x in the integral by the Lagrange interpolating polynomial. Okay, so my integral I is the integral from a to b of f of x dx. And instead, this is going to be the integral from a to b of my Pn of x dx. But that's just the integral from a to b. And now I'm going to have the sum I equals 0 to n of Li of x times f at xi dx. Okay, now you can see that the sum and the f of xi's do not have anything to do with x. So I can pull that out. All right, so when I pull that out, I get that I can take out the sum I equals 0 to n, the f of xi, and then I get the integral from a to b of Li of x dx. So now I have these things, and this is what I'm going to call my weights. So this piece right here I'm going to call that my WI. Okay, so these are the integration weights. And if I know what those are, then I have a formula. Okay. So this goes back to saying what I just said before earlier, that this is then equal to the sum I equals 0 to n of f of the xi's times their weights, wi. All right. Now, wi is hefty. Every wi is the integral from a to b. In the numerator, I have x minus x naught, x minus x1, all the way down to x minus xi minus 1 times x minus xi plus 1, all the way down to x minus xn. And then I divide that whole thing by xi minus x0, xi minus x1, dot, 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 xi minus xi minus 1, xi minus xi plus 1, all the way up to xi minus xn dx. So that's a pretty big deal. Okay. All right, so let's go ahead and derive what happens when n is 1. Okay, so one. We get the derivation when n is equal to 1. Any questions, guys? Okay. All right, so we get I, the integral from a to b, f of x dx is going to equal, I'll be approximately the integral from a to b of p1 of x dx. Okay, and here x naught is a and x1 is b. All right, so this is the integral from a to b, and I'm going to have L0 of x times f of x naught plus L1 of x times f of x1. All righty. So we already said we can pull the f of x naught out. We get the integral from a to b, and L naught is going to be x minus x1 divided by why you want over x naught minus x1 dx plus f of x1, the integral from a to b of x minus x naught over x1 minus x naught dx. Okay. So this is f of x naught over x naught minus x1 times, I feel like I'm missing a 2. Okay, x minus x1 squared over 2 plus f of x1 over x1 minus x naught times x minus x naught squared over 2. And this is evaluated between A and B. So now I get f of A over A minus B times x minus B squared over 2. That's why I can't do this. Plus f of B over B minus A times x minus A squared over 2. That whole thing evaluated from A to B. And I will spare you the algebra. This actually comes out to be B minus A over 2 times f of A, f of B plus f of A plus f of B. Oh my goodness, that's the trapezoidal rule. So now we see when n is equal to 1, we get the trapezoidal rule. Okay. So what's the error in this formula? So now we can actually find the error for the trapezoidal rule because we know the error for the Lagrange interpolating polynomial. If we integrate that, we know the error in the integral. Okay, so the error in this formula well, we know that f of x is equal to p1 of x plus the second derivative. So this is going to be, this is p1. So this is going to be the second derivative of c over 2 factorial times x minus a times x minus b. So therefore, the error in the integral is going to be the integral from a to b of f double prime at c over 2 factorial and now I'm going to get x squared minus ax minus bx plus ab dx. So I can pull out the f double prime at c over 2. And now I get this integral. I get 1/3 x cubed minus a over 2, a plus b over 2, x squared plus abx evaluated between a and b. This turns out to be the second derivative at c over 2 times oh boy, am I going to write all this out? No, I'm not writing all this out. How much time do I have? I'll write it all out. It's irritating. Okay, b cubed over 3 minus ab squared over 2 minus b cubed over 2 plus ab squared minus a cubed over 3 plus a cubed over 2 plus a squared b over 2 minus a squared b. Okay. Then this turns out to be f double prime c over 2. And then this turns out to be minus b cubed over 6 plus 1/2 ab squared minus 1/2 a squared b plus a cubed over 6. And believe it or not, that's so beautiful. It turns out to be f double prime at c over 2 times a minus b cubed over 6. So now we have a nice closed form for the error. It is minus f double prime of c over 2 b minus a, I'm sorry, over 12, b minus a cubed. Okay. So now our trapezoidal rule formula is now the integral I equal to integral from a to b of f of x dx is equal to b minus a over 2 times f of b. Okay. This is plus f of a minus f double prime at c over 12 times b minus a cubed. Okay. All right. What do you think we're going to get if we do the derivation for n equals 2? What do you think we're going to get if we do the derivation for n equals 2? Anybody still on this call, on this class, in the class?
Yes.
Oh, okay. What do you think we're going to get? We did n equals 1. We got trapezoidal rule. If we do n equals 2, we're going to get Simpson's rule. Okay. I will see you guys